we have to find the at this point P, which is on axis of a current carrying coil. So this is a current carrying coil in which this high current is flowing, and we have taken a small segment of this that is of length dl, right? So this is the current element. So current element will be what? It will be I into dl, right? Now, as per Biot-Savart's law, this dB, which is magnetic field at P due to this small segment dl, the magnitude of that dB will be given by mu naught divided by 4 pi I dl sine theta divided by r square. R is actually the distance between the current element and the point of observation. So suppose this point is O, then that is OP. OP is the distance, and that we have represented here as S. So let us write that as S square. Right. Suppose this distance is X, that is from C to P, it is at X distance, and R is the radius of the, suppose this R is the radius of the coil. Now what is theta? Theta in this expression is angle between dl, which is at the top. So that dl and the distance, right? So we know that this theta is actually in this case, because this dl is perpendicular to s, the distance. If we take it as vector, then they have direction, and now this dl is perpendicular to s. Right? It will be always perpendicular to, and then this line, the green line, which is dl, and the OP, these two lines are perpendicular, right? So that's why this means what? Theta is equals to 90 degree, and that's why sine theta will be equals to 1. So this dB magnitude is equals to mu naught by 4 pi I dl, sine theta is gone, divided by s square. This is the magnitude of dB, and this here you see that this is the direction in which dB will be there, right? So that is dB direction, and this is the magnitude, and this dB is due to one of the very small current element IDL, which is right now at the top, and we have seen that if we take a current element at the bottom that is symmetrically opposite point, same current element, then again from this you will have a magnetic field, small magnetic field, and that will be in this direction. So there will be multiple magnetic fields, and all these fields are actually vectors, so we have to keep on adding these vectors. Now you have to add these vectors, and you can see that these vectors are in different directions. So best way to do that is that you draw a axis here, and then we resolve it into components. Now we can take whatever angle we want. Right now, suppose I take that this dB is at angle phi with this y-axis. So if that is the case, then it will have two components. This component will be dB cos phi, and this component will be also dB cos phi, that is of these two different vectors, and the component here of the two will be dB sine phi of both. So what do we observe here? The dB sine phi will get added, but dB cos phi and cos phi will cancel. So the vertical components will cancel each other, while these dB sine phi, that is the horizontal component, that is component along the axis, they will add up. So in order to find the total or the resultant magnetic field, we see that the field dB lies in the plane of paper and is perpendicular to S. This dB, right? The dB which we see here, this dB or this small magnetic field, these dB and S are also perpendicular. dB is also perpendicular to S. So you will have to imagine this in 3D. So this ring is in such a way that half of this ring is on top of your screen and half of the screen, that is in top of your screen means in front of your screen, and half of that is on the back side of your screen. So the line S which you see here is the line S, means this O to P, or the distance S, the vector S is actually what you see here is in the plane of paper, and dB lies in the plane of paper, and that's why it is perpendicular to vector S. Right? So this dB is perpendicular to S. Angle between dB and S is 90 degree. So now we consider this phi angle between the S and R. Right? That is this angle. And this phi and this phi are same. So dB can be resolved into two rectangular components, which we have already done, that is dB cos phi and dB sin phi, and we have seen that the cos phi component gets cancelled, which is the vertical component, and there is only component along the axis of the ring or the coil. So now what do we have? Now we have to find this sin phi. That what is sin phi? So this sin phi, the complete or the total resultant B or magnetic field will be equals to integration of dB sin phi only, because the cos phi components are cancelling each other. So now we have to find what is sin phi. Now from the figure itself we can see what is sin phi. If that angle is phi, even this angle will be phi, and sin phi is nothing but R by X, right? So sin phi is equals to R by X, right? So this B can be written as dB. We have already seen that is this mu naught, integration of mu naught by 4 pi I dl divided by S square into R divided by S. Right. So now S dl R, or with everything is there. Now we have to integrate this. So this can be written as mu naught divided by 4 pi I R divided by S cube, S square into S is S cube, into integration of dl. That's all. And dl is actually what? Dl is the small segment of length on the circumference of the ring, so that's why it's total integration will be 2 pi r. So this will be equals to mu naught divided by 4 pi I into r divided by s cube into 2 pi r. So this gives us mu naught divided by 2s cube into I r square. This is the magnetic field. Only thing is, what is S? So S is equals to this S here. S is equals to r square plus x square root. So this to the power 3. We will now just put that, and this b will come to mu naught divided by 2 r square plus x square whole raised to power 3 by 2, and in the numerator I into r square. This is the expression for magnetic field. We have got the same expression yesterday also, but in the derivation part there was some problem, right? And other cases remain same. That is, if there are n different or total n coils, then the B becomes mu naught into n I r square divided by 2 into r square plus x square to the power 3 by 2. This expression is when there are n coils present in the, or there are n turns in the coils, right? And the special case we have already seen, that is at the center. So if it is at the center, obviously this x will be equals to 0. So we have to substitute x equals to 0, and the value of b which we get is mu naught n I, we have r square divided by 2r cube. So this is mu naught ni divided by 2r. This is one value which we get, that is mu naught ni divided by 2r. Now if you see here, there is r square there on the top, and we also had pi. Somewhere we had pi, right? So if I multiply up and down, I mean the numerator and denominator by pi, that is multiplying numerator and denominator by pi. Just wait for some time. Yeah. So now if I multiply this numerator and denominator by pi, this b in case of center becomes mu naught ni pi r square divided by 2 pi r cube. Now in this pi r square is actually equals to cross section area of the coil, right? And this we will represent as capital A. So now B will be equals to mu naught ni A divided by 2 pi r cube. So this is the same B but expressed in terms of area. This A is area of the coil, right? Okay. Second special case, case number 2, that is at the axial point but lying far away from the coil. That is when this x is very, very, very large as compared to radius of the coil. So the point of observation is very far from the coil. In that case, wherever x and r are getting added or subtracted, we should ignore r in comparison to x, or we can say that r can be replaced with 0. That is only when x and r are getting added or subtracted. So where is that happening? That is happening only here, right here. R and x are getting added, and because r is very less as compared to x, so even r square will be very less. It will be lesser because mostly it will be in fractions, right? So this can be written as our original expression is b is equals to mu naught n I r square divided by 2 into r square plus x square whole to the power 3 by 2. This was our expression. So we said x is very large as compared to r. So here only in denominator we will put r is equals to 0, not here, because here it is significant, it is getting multiplied, but in the denominator it is getting added, so it is insignificant. So from here, if we remove r, it becomes mu naught n I r square divided by 2 x cube, right? So that is the magnetic field at a point when or where the distance of the point from the from the center of the coil is very large as compared to the radius of the coil. There is one more special case, sometimes it is being asked, that is when x will be equals to r, that is at a point whose distance from the center of the coil is same as the radius of the coil. In that case, b will become mu naught n I r square divided by 2 into r square plus r square to the power 3 by 2. So if you simplify this, it becomes mu naught n I r square divided by 2 into 2 to the power 3 by 2 into r cube. So this again simplified, it will give us, if we simplify this again, it will give us mu naught n I divided by 2 to the power 5 by 2 into r. This is your last special case, right? And then we have already seen about the directions and all, so that is already done. So this is first application of Biot-Savart's law. Any doubt in this? Okay, let's see some other applications of Biot-Savart's law. The next application of this law is in finding the magnetic field due to a long straight current carrying conductor. So our next topic is magnetic field due to a straight, long, straight current carrying conductor. Now this is also important because the result of this topic we are going to use again somewhere later in the chapter. So that's why this topic is actually very important. And there are two related topics to this, and mostly you will also have viva questions based on this. So this is very important. Now again, this is application of Biot-Savart's law. So what do we have here? We have a straight current carrying conductor, right? And it's a straight line. It's a straight linear current carrying conductor. So suppose this is the conductor, a straight conductor carrying current, and let the direction of current be from bottom to top, that is upwards. So let this be the direction of current, that is going upwards, right? Let us say this is point X and this is point Y, the top end is point Y. Suppose this is the point P, this is point P where we have to find the magnetic field. Now this point P will be at some distance with some distance from this linear current charge. Let that distance be this, right? So this is the distance. Let the distance be X or A or whatever. Suppose we say that that is given by A. So A is the distance from the between the current carrying conductor and the point P. So we have to find magnetic field at that particular point. We know that I current is flowing in this segment. Now, in order to find that, what we do is we consider a very small segment of current. Let this be the small segment of current or R current element, that is IDL. So I current is flowing in this, and let this DL be the length of this. So if that is the case, and suppose this DL is at distance L from this point, this point, let us say is Q, that is the foot of the perpendicular from P on the current carrying conductor, right? And let that be a distance L from the, so at distance L there is a current element TL, right? Now from this, due to this DL, there will be a magnetic field at P, and we know that the magnetic field at P due to this current element DL will be given by the Biot-Savart's law, right? So, and if we say the, if we consider the direction of the magnetic field, the direction of magnetic field will be like this. So this is the small magnetic field dB due to the current element dl. So what will be the magnitude of this dB? This dB will be given by mu naught by 4 pi I dl sine theta divided by r square. in this expression, what is r square? R is the distance of dl from the point of observation. So let us say this is our r, that is the current element and the point of observation and the distance between them. Let us say this point is O, right? And what is theta? Theta is angle between dl and r. So this is theta, correct? So that is dp, that is mu naught by 4 pi idl sine theta divided by r square. Now we have to find this sine theta. Now sine theta is, here it is simple, it is a divided by r, where a is the distance of point from the wire and r is the distance of point from the current element, right? So sine theta is equals to, in this case, it is equals to a divided by r. Okay. Now when we will be integrating, that is when we'll be finding the total magnetic field, so we have to consider all these small dl or the current elements from here. That is, on this segment there will be many such small dls which we'll have to consider, and then we'll have to add. That is what integration is. So basically we'll be doing integration from this point x to this point y. Now how to do such integration? So in this case we'll think about that, what the limits, we'll have to think about the limits from where to where this limit will change. So I cannot take anything in terms of the length, because this length of this wire is unknown, right? And we don't have an idea from where to where it will stretch. So we have another quantity which we can measure, that is this angle of top from the point of observation and the bottom, this end, to the point of observation. So when we move from x to y, even this angle will change. Which angle? The angle this particular angle, the phi, angle phi will change. So this we will name it as angle phi 1, that is the lower limit, and this is the upper limit, say phi 2. That means now instead of writing or our expression in terms of theta, we should have our expression in terms of phi. Let this angle be phi. So phi is, for clarity, let me write here, phi is angle QPO. This is angle phi, right? And now our expression, or now the expression which we have, if we can write that in terms of phi, we will have a variable which varies from phi 1 to phi 2. Otherwise we don't have any value, limiting value for this, that what is the lower limit of this length or this, or what is the lower limit of theta and upper limit of theta, that we don't know. But now we know that we can apply a lower limit and upper limit to this phi. Phi is this angle between angle subtended by the top and bottom ends on the point, right? So that's why here also we'll have to take that angle. So here we have taken this angle phi. Phi is angle between, again, the Q, P and O. So that is angle phi. Now this angle phi and theta are complementary angles. That means sine theta will be equals to cos phi. So this dB now can be represented in terms of phi. What will be that? dB is equals to mu naught divided by 4 pi I dl divided by r square. Instead of sine theta, I'll write cos phi, and the value will remain same. The only thing is now our expression is in terms of phi. So this is cos phi, which is equals to a by r. So this is also equals to a by r. The value doesn't change. So but we have the expression in terms of phi, and now phi is a variable which changes from phi1 to phi2. And in order to find our, and that's why I'm not writing here a by r, because this r is a variable now, right? So now, so this cos phi is equals to a by r, which we have already written. So this r will be equals to a sec phi. So now we have r in terms of phi. So we don't need these two values, right? So this, if I change the location of dl, r will also change, right? And phi will also change. So, but we have learned integration only in terms of one variable, that is either r or phi or x or y. But here we are having two variables or two unknowns, that is r is also variable and phi is also variable. So either I change r to phi or phi to r. So that's what we are doing here. R is equals to a sec or secant phi. So r becomes a secant phi. And what else we have? We have tan phi. Later we'll use it. So tan phi will be equals to L by A. We may need it later, so I'm just writing it like that. Right. So in that case, even L, because L is also a variable, right? Because we have here DL. Our expression is in form of DL. I mean L. So L has also to change. So L will be equals to A tan phi. Done. So if L is a tan phi, what is DL? Because we have to replace this DL. So DL will become a secant square phi, because tan theta's differentiation is secant theta, and d phi. This technique of integration you will learn in mathematics. So I'll explain that there as well. So now we have dB, and dB is equals to this. Now this DL and r square has to go. Right? So this dB can be now written in terms of a function of purely phi. So that is mu naught divided by 4 pi into I as it is. Then dl is a secant square phi d phi, that is dl. Then we have cos phi divided by r square. Now r is again in terms of secant phi, so that is r is a, this is our expression. So what do we see here? Is a square a gone, secant square phi gone. So our dB is now simplified to mu naught by 4 pi a. A is what? The distance, that is constant. Remove it. And I, and then just cos phi d phi. So only that is the variable, that is cos phi d phi part. Others are constant. So now in order to find the total magnetic field, that is B, we have to just integrate this dB from phi is equals to phi1 to phi2. But phi1 is in opposite direction, so I'll say this is minus phi1, and phi2 is in opposite direction. So if phi2 is positive, phi1 will be negative. Right? So this will be equals to mu naught I divided by 4 pi a integration of cos phi d phi from minus phi 1 to phi 2, and cos phi's integration is sin phi. So this is mu naught I divided by 4 pi a, cos phi's integration is sin phi, and the limits are minus phi 1 to plus phi 2. So that is equals to mu naught I divided by 4 pi a into sine phi 1 plus sine phi 2, because this will be minus of minus sine phi 1, that will be equal to sine phi 1, that is positive, and plus sine phi 2. Now this is the expression, or this is the final expression of magnetic field due to a straight long current carrying conductor at a point P, which is at a distance A. So what do we have to do? We just have to measure this angle phi 1 and phi 2, which are the angles subtended by the end of that long current carrying conductor with that point P. Right? So that's about the expression, the final expression, and obviously we'll have some special case here. The first special case and the most important case is when this is an infinite long wire. So we don't have the length here, but we have the phi. So this, in that case, phi 1 will be equals to phi 2 will be equals to pi by 2. That is the infinite long wire case. And you just substitute that there. So in that case, this B will become mu naught I divided by 4 pi A into 2, which is equals to mu naught I divided by 2 pi A. This is very important case, and this is the expression we will be using it again and again, right? And there will be other cases as well, that is one angle is 90 degree, one angle is 0 degree and all. So that is when one angle will be 90 and other will be 0, when this point of observation is here, right? And this wire is infinitely long, so one angle, that is phi 1, will be 0 and the other angle will be 90 degree, right? So that is this case. And there can be other cases as well, that is infinite of when it has a finite length, but the L, the point which we are finding, where we are finding, that is at the midpoint of the two ends. So that is about this topic, the two topics which we have seen today and the derivation of that. In the next class, which is tomorrow, we'll see, or we'll continue. We'll see what we have to do tomorrow. I think tomorrow it will be chemistry.